Okay, so now I'm covering what we call finite horizon dynamic programming, and this is in discrete time. We can, by the way, use the Lagrange to solve this, but that's an inefficient method. So we're going to use the Bellman equation instead. So suppose the question is to maximize the present value of lifetime income, but in this case we don't have two time periods. So for instance, if it was just from 1 to 2, that would have collapsed to the same question we just did, like this one, the two period consumption model, in which the only concern was a current period and a future period. However, in this scenario, there are more than just two time periods. The time period lasts from time period 1, 2, 3 till the uh, T time period, capital T. And all of these time periods are being discounted. Okay, so basically, the first step is to identify the state and control variables. As you can see, the utility actually depends on current consumption in that time period. Therefore, what is in our control? The control variable uh, is consumption, and the state variable is what you get unbound with, and in this case it's assets or whatever amount of saving that you have. And so therefore this is being denoted by AT. Okay, so first of all we need to state the Bellman equation itself. So the Bellman equation is as follows. Okay, so the utility at time period AT depends on the state variable at time t, and it is when you maximize the utility in that time period and also all the time periods that come afterwards. This is done by doing backward substitution, and I'll probably make another video explaining what this equation itself represents, because right now we're just doing mathematics without actually understanding what's happening. But we can solve the traveler's problem or some other problem to actually show what this equation means. Okay, for now we're just going to do the mathematics without getting into what this equation represents. Okay, so since the control variable is c, I'm going to take the derivative initially with respect to ct, and I'm going to put it equals to a 0. So since u does depend on ct, I can take the derivative with respect to ct, but vt plus 1 doesn't directly depend on ct, so we'll have to use the chain rule. It depends on, we'll have to take the partial derivative first with respect to at plus 1, and then at plus 1 is what depends on ct. Okay, so this is simply the derivative of u with respect to ct plus 1 plus rho derivative of v with respect to at plus 1, and the derivative of at plus 1 with respect to c1 is just a 1. So therefore we have the following expression. The first derivative is equals to 1 over a 1 plus rho at plus 1. So this is our equation 1. Next, we take the derivative of the Bellman equation with respect to the state variable. And in this scenario, utility doesn't depend on at, so that's a 0. And we have a 1 plus rho. And vt plus 1 actually depends on at plus 1, where at plus 1 depends on an at. So the derivative of if I lag this one period forward, I'm going to get an at here. So the coefficient is the derivative. So I have a 1 plus r there. So this, actually let me rewrite this as the derivative of v with respect to at plus 1, and then I have a 1 plus r here. Okay, so overall my expression becomes the derivative of v with respect to at is equals to 1 plus r over a 1 plus rho v and at plus 1. This is my equation 2. And if I actually lag this one period forward, I'll be left with actually what I should do is wait, the derivative of VAT over VAT plus 1 is equals to 1 plus r over a 1 plus rho, right? So put 1 into this, 1 into this. So in the denominator we can see that we're going to get, if I make this the subject, the derivative of v with respect to at plus 1, I'm going to get 1 plus rho into derivative of u with respect to ct. Okay, and what about the derivative of v with respect to at? It's the same thing, but one period, it's just lagged behind one period. So have a 1 plus rho derivative of u and lagging behind one time period. Okay, the right hand remains the same. 1 plus rho and 1 plus rho gets eliminated, gets cancelled out, and we have the expression, the derivative of u with respect to ct minus 1 over derivative with respect to ct 1 plus r 1 plus rho. Since we actually when we're talking about intertemporal consumption, we're concerned with today's consumption and the next period consumption. So I'm just going to lag this one time period forward to get a ct in the numerator and a ct plus 1 in the denominator. So this is visually easier to understand that we have two time periods. One is the current and one is the future. Okay, so therefore the derivative with respect to ct plus 1 is 1 plus r over a 1 plus rho, and then the derivative of ct plus 1. Okay, so this is the Euler's equation which you are expected to derive. And actually this is, you can either call it the Euler's equation, or I like to call it the tangency condition. So this is the tangency condition, and what you need to do is that this basically helps you find the optimal level of consumption because you solve it simultaneously. So solve this and the intertemporal budget constraint simultaneously to obtain the optimal level of current and optimal level of future consumption. So you can solve such a question, like you can get proper optimal points only if the utility function is given. So suppose the utility function is ln c, so you know that the derivative with respect to c is a 1 over c. So then our Euler equation becomes a 1 over ct, or you can just say c1, and 1 plus r over 1 plus rho 1 over c2. And from here you can make you can make C2 the subject, 1 plus R over a 1 plus rho into C1. So again, just like the previous question, you get C2 in terms of C1, and you just need to put this into the intertemporal budget constraint, which was the present value of lifetime consumption. It should be equals to the present value of lifetime income. So this is the present value of lifetime consumption, and this is the present value of lifetime income. So when you solve this equation, you solve 3 and 4. I'll label this as 4 simultaneously. You will get the answer. Solve 3 and 4. So that's it for this question. Sir had put another question. I believe it was about finding the optimal level of capital. I'll solve that one as well, but in the next video. I hope this lesson was useful, and I'll see you in the next one.